Okay, class. Good evening. Can y'all hear me? Can y'all hear me loud and clear? Can you hear me loud and clear? Can or not?
Yes.
Oh, okay. All right. Yeah, because today I had some meetings, and then some people said that my voice was very soft. So I want to ask y'all, is it okay? Huh? Okay, so looks like the microphone is okay. Yeah. So let's continue with our last tutorial. So we have been doing this partial differential equation, right? And you're looking at the summary of methods here. So far we have done direct integration method. Okay, yeah, we did direct integration method. And then let's see this direct integration method now. So it's for PDE that contains only one derivative term. Okay, only one derivative term. Yeah, so it's suitable for that kind of PDE. And then last week we also talked about this separation of variables method, right? Now this method is for another kind of PDE, and it's what kind? It's a linear PDE, and it must be homogeneous. All right, linear and homogeneous PDE. And if there's a boundary condition given, then the boundary condition must be homogeneous. Right? Yeah, so it's like that. So tonight we are going to talk about this Laplace transform method. And what is this kind of method for? Well, it's for a linear PDE. All right, so it has to be linear. And then with this condition, it must be invariant in at least one independent variable. Okay, can be invariant in both independent variables, but at least must be in one. All right, yeah, so it's like this. So let's go and look at this Laplace transform method to see what it is about. So here it is. So solving this linear PDE by Laplace transform. All right, so this is what we have here. So what we are having here is first we look at the key idea. All right. Well, the key idea here is actually from this property. All right. So we know that if we have this derivative of f with respect to t, if you go and Laplace transform, right? So that means Laplace transform of f prime t, then we know that it is s, and then Laplace transform of ft, and then minus f0. So actually it's this, all right? S capital Fs minus f0. So this one we know. So from this formula here, we can see very well that, you know, if you have a derivative term, let me see my highlighter. Wait, see my highlighter, what color is it? Oh, it's yellow. So let's change to a different color. Maybe we change to a darker yellow, right? Yeah. So this one here, so we notice that after Laplace transform, you know, here you have a f prime t, right? But after Laplace transform, there this is what you have. So it's a s fs minus f0. So you find that after Laplace transform, in the s domain, there's no differentiation term. Okay, so you realize that you don't have the d dt anymore. All right. So, well, then we realize that, oh, looks like, you know, Laplace transformer can remove the derivative term. All right, so this is actually the idea behind. And actually, we use this idea that, you know, using Laplace transform, you can remove the derivative term. We use that idea in the ordinary differential equation. So it's our previous tutorial. All right, so we use Laplace transform to solve ODE, right? So actually over there, we go and Laplace transform the whole equation, yeah, so that the derivative term with respect to t all disappeared. Okay, so we see that this is what we do in ODE. So then we wonder, can we also do this in PDE? So the answer is actually yes. So in PDE, we can also apply Laplace transform. All right, now PDE, you know that we have at least two independent variables, right? Now, suppose you can Laplace transform one of the variables, for example, t, into the s variable. Okay, so if you go and do this Laplace transform, with respect to t, then you will find that there will be no more derivative respect to t. So the differentiation with respect to t are eliminated. Okay, so you only left with s. Now you still have another independent variable, right? Now that independent variable may have derivative, but that's okay, because now what remains is an ODE, becomes ordinary differential equation, respect to the other independent variable, for example, x. All right, so then you can just solve it like ODE. So that's the point. Okay, now, all right, so basically, after your Laplace transform, you're hoping that you can transform the PDE into ODE. All right, transform PDE into ODE. Yeah. So actually, I summarized it here. Well, you can see that this one is I write my own one, right? So solving linear PDE by Laplace transform. So actually, you see these are the main steps. Yeah. So the first step is you got your PDE, right? So suppose these are your independent variables. So you got x, you got t, right? So what you do is you go and Laplace transform the whole equation. Now, when you Laplace transform, you must Laplace transform respect to the independent variable that the PDE is invariant in. All right, that the PDE is invariant in. Now, suppose it's invariant in t. Then you go and Laplace transform respect to t. So if this is the case, that means after Laplace transform, your this t now becomes what? Now becomes s. Okay, yeah. So from t now you change to s. Now the x, the other independent variable, that one no change. Okay, so x here still x. Is that right? Okay, so after you reach here, you won't have derivative in t anymore. All right, so here you have no derivative in t. All right, so maybe I type here. Am I able to type there? Let me try, Oh, okay. So here you won't have no derivative term in t. All right, so here you won't have any derivative term in t. So that's why you're only left with derivative in x. All right, so you're left with derivative in x. So therefore, you can consider it as the ODE. Okay, yeah. So your ODE is in x. So then after that, what you do is you go and solve the ODE. Okay, it's the ODE, the independent variable there is x. Then you get this solution here. Right, so you get this solution, which is a capital U X S. Okay, so that's capital U. So what we do next is that our capital UXS, you must change it back to XT. All right, so what we do here is you inverse Laplace transform with respect to this S here. Okay, so when you do it with respect to this S here, then the S there will change back to this T. Is it okay? Then you get your solution already. So this one is your solution. All right, cannot, yeah. So this is the main idea of this Laplace transform method. Okay, now, yeah. So now, let us go and see. Let's go and see how we do this. So maybe we go to our tutorial questions. Yeah. No, we are not here. We are at number 3 now, right? So this is number 3. So we want to use Laplace transform, solve the following wave equation. All right, so this is our equation. So over here, our x is from 0 to 1. The time t is more than 0. Okay, subject to this boundary condition. Well, you can see that it's a condition on x, right? This one is when x is 0. Okay, and this condition is when x is 1. All right, so that's why we call it boundary conditions, right? When x is 0, when x is 1. All right, and we also have this initial conditions. What's the meaning of initial? Initial means the time is 0. So that's why you see here ux 0, right? Time is 0. And then this one is del u del t. differentiate respect to t, and then you substitute the t as 0. Okay, so that's also initial condition, right? Now, okay, so you want to do this, right? So you want to say, they say use Laplace transform. Okay, let's go and check our summary. Summary actually is here, right? Yeah. So Laplace transform is not here. It's in front. Yep, here. So we see Laplace transform method now. When do you use this? So for linear PDE, linear, and must be invariant in at least one independent variable. Okay, so it's like that. Now, if we go back to our question, we see whether is it linear, is it invariant in one independent variable? All right, so let's see. Is this thing linear? This one linear or not? Now, class, is this linear? Linear? Is it linear?
Yes.
Yeah, it's linear. It's linear in U. All right, remember linear? Linear means only U, right? Only U. So we find that each of the terms is only U. You don't get things like U times U, right? So it's linear. And is it also invariant? Is it invariant or not? Invariant? Invariant? Remember what is invariant? You look at the coefficients of the U term. Coefficients of the U term, you see here, coefficient constant. Here, coefficient also constant. All right, so it's invariant. All right, in fact, invariant in both. Invariant in T and X. So in fact, invariant in X also. All right, so what we need is just invariant in one. Invariant in one is enough. All right, so this one is suitable to use Laplace transform method. All right. So let's go and look at our summary, how to start now. Summary is on which page? Let's remember the page, page 7. Okay, so let's remember this. And we now go to our solution. Wow, so many files. Is it this one? Okay, yep, so this is the one. All right. So our first step there is you want to Laplace transform, right? Respect to the independent variable that the PDE is invariant in. Well, just now we know that the PDE is invariant in both T and X. All right. Now, since we always, all the while we are like conditioned like that, Laplace transform is respect to T, right? So let's go and do respect to T. So if we go and do respect to X, maybe suddenly our mind cannot turn towards that, right? So since it's invariant in T, let's do with respect to T. All right, so we say we'll take Laplace transform with respect to T. Okay, right. Okay, now before we carry on, let's get our notations correct here. So these will be the notations that we are using. All right, so our unknown function is uxt. And when you Laplace transform this uxt with respect to T, we get a capital U as x. All right, so is this okay? All right, so this is our capital U as x after Laplace transform of the small u. Okay, so noting this, now we Laplace transform the whole equation. And this is what we'll obtain. All right, so this is what we have. Let me bring my highlighter. Hey, so first of all, you got this term, right? So you want to Laplace transform. Now this one Laplace transform actually will give me this one here and this one. Okay, yeah, this one Laplace transform will give me this. Then you may wonder, how does this come about? Now actually it's from our formula. And then you see, I got my formula here. Now, this is what we know, right? When we were doing PDE that time. Laplace transform of y prime t is like that. Laplace transform of y double prime t is like this. Now, of course, here, small y, big Y has this relation here. Okay. Laplace transform of yt is a capital Ys. All right. So now, what we are having here is del square u del t square. All right. Of course, this is partial derivative. but we can still make use of this formula. All right, so when you make use of this formula, it is I'm making use of the first formula, right? So you got your s square, right? So then you see our s square here, and then the next term is what? Capital YS. Now here capital YS means Laplace transform YT, huh? So at our side, it will be capital U XS, right? So we're done with this. And then minus S, now you see here minus S, right? And then here is a Y0. Okay, small y0. So in our case, it will be the small u at x at t equal to 0. So therefore, it's a ux0. All right, so that's the second term. And finally, you minus y prime 0. Okay, now y prime 0. The y prime, the prime here means differentiate respect to t. All right, so in our case, it will be del u del t. And then substitute the t as 0. All right, so therefore this one is this. Is it okay? Any questions? Yeah, so this one all right, all? Yeah. Then let's do the right hand side. Now your right hand side is del square u del x square. Now how you Laplace transform with respect to t. Now since this one is respect to t, so your del square del x square is not affected, still there. All right, so that's why you see here you got your del square del x square. What you do is you just go and Laplace transform the small u, and that will give you the capital U X S. Right, so that's why this one will give me this one here. Okay, right. So this one okay, y'all. So now we see that we have two initial conditions. There's a ux0, there's a del u del t x0, right? There are two initial conditions. They are actually given. All right, so in our tutorial, they are actually given. Now you can see here, these two here, over here, these two initial conditions, right? So now you just go and use it. So you put inside. After you put inside all, this is what you have. Okay, you put this inside, then you get this. Is that okay? Yep. Now I want you to look at this. Look at this line here. Now over here, you can see that there's no more t, right? Yeah. There's no derivative in t. What you have is only derivative in x. You only have the del square del x square, right? So that is the only derivative term. So it's only derivative in x. So therefore here, you can say that this one is a ODE in x. Treat it like a ODE in x. Is that all right? All right, all? Yeah, ODE in x. Yeah. And then another thing is, let me go and bring all the terms to one side. I mean, at least bring this term to this side. So all the u term together. Okay. Yeah. So that is what I have. All right. So this one is an ODE in x. It's an ODE in x. Okay, because you only have a derivative in the x term. So this one definitely is ODE in x. And this is a non-homogeneous. Okay. It's an ODE in x and it's non-homogeneous. Let's see whether I write it here. Oh, I didn't write the non-homogeneous. Okay, this one is a non-homogeneous. Non-homogeneous. All right, it's a non-homogeneous ODE in x. Okay, in x. All right, non-homogeneous. Non-homogeneous because you have this term here. All right, it's due to this term. This is a non-U term, right? Yeah, so that makes the equation non-homogeneous. Yeah. So now what we do is, let's see our summary. Let me say, then you go and solve the ODE. So this is an ODE, right? So you go and solve the ODE. So we are supposed to get this solution UXS. And the UXS here, this will be, you want to get the solution of that. Okay, yeah. So this ODE is an ODE in x. X is the independent variable, okay? But of course here, you also see the s, right? Because you see UXS, right? So s. So what is the role of s here? Well, the s here actually is considered as a constant. Is it okay? All right, all? So now let's go and solve this non-homogeneous ODE in x. So this del square del x square will be treated like d square dx square. So it's a second order ODE. All right, yeah, second order ODE. Then of course you all know how to solve, right? I think a few days ago, so don't know yesterday or not. Yeah. So I email you all this, right? Yeah. And how to solve second order linear ODE, right? So you do all these things. Okay. Yeah. So here your S square is like constant. So to solve this, you need to consider homogeneous solution and non-homogeneous solution. Okay, yeah. So I put the ODE here. Okay, now we go and solve. So first of all, I will consider homogeneous equation. Because to solve this, you actually need two solutions. One is called homogeneous solution, then another one is called particular solution. Then you add them up, and that will give you the general solution. Okay, so this one you actually learn last semester. Yeah. Okay, so let's consider the homogeneous solution. So homogeneous solution means now instead of having this term here, you just put it as 0. Okay, and of course my UH. Now see all this UH, right? I don't write U, I go and write UH because the H stands for homogeneous. Okay, yeah, so that's it. So let's go and solve this. All right, so using this one here, you go and get what characteristic equation and so on. I can see that here, if you go and solve, your roots will be plus minus s. Yeah, your roots will be plus minus s. Okay, yeah. So I think you will get the distinct real roots. Okay, so that's your case 1. Okay, so you go and do that. And therefore, this is your general solution for this homogeneous equation. So actually, it's case 1 here. All right, so that's our case 1. Then the next thing is, so we stop here for a while, and we go and get this particular solution of this ODE. All right, so this is our homogeneous solution, right? K1, K2, of course, are constants, unknown. Okay, let's go and find particular solution. So this particular solution actually is how to find it is you need to look at the right hand side here. Okay, look at this right hand side here. You see this minus psi pi x, and then you let your particular solution be something of a similar form. All right, so therefore, I can let it be CS, C is a constant, psi pi x. Okay, constant times psi pi x. Now, CS is a constant. Why we put bracket S is saying that this constant may involve S. So that's all. All right, and you know why we call UP, right? Because the P stands for particular. Yeah, so it's like that. No? Okay, now here the C constant, right? So now I want to find this C. Okay, now how to find it? Now, since this one is a particular solution, right? Particular solution. So meaning it has to satisfy equation 1. So let me substitute this UP into equation 1. So the whole equation should hold. All right, so how to substitute there? So that means you take this C times psi pi x. You go and differentiate respect to x 2 times, put in, and then minus s squared, then substitute the u inside, then equal to minus psi pi x. So that is what you will get. Okay, go and differentiate respect to x 2 times. This is what you will have. Then the other one is substitute, and then equal to this. Okay, so now our aim here is to find the constant C. So I think we can group the psi pi x both sides. And then we can compare the coefficient of psi pi x. Yep, then you see I group together. So this tells us that this C pi square plus S square must be 1. All right, it should be the same as here, should be 1. So therefore from here, I know that this is the C. All right, so you see I found C already. So this is C, and you can see that your C is in terms of S, right? Yeah, so it does involve S. So we note that it involves S. Okay, so it does involve S. Okay, it can involve X, not say mass, but it can involve S. And here we find that it does involve S. Okay, yep. So now with this C here, now you put into your particular solution. Okay, so therefore now your particular solution is like this. Right now? Okay, so now you got particular solution already. And what I'm going to do now is I want to get the general solution. Wait, my highlighter. My highlighter. Oh, here. So now I get the general solution of 1. Okay, general solution of the ODE. So this general solution is homogeneous solution plus particular solution. All right. So now we just go and add them together. This one over here is your homogeneous solution. Then this one over here is your particular solution. All right. Okay. So add up already. Then what? Have we found UXS? Is this our UXS? Have we found the solution already? Yeah. Say solution is UXS, right? So have we got the solution UXS? Are we ready to do inverse Laplace transform? Class, what do you think? Not yet. Okay, not yet, because still got some unknown constants. Then you see your K1, K2 still unknown, right? So therefore, now you must go and find K1 and K2. All right. Only after you get your K1, K2, you put inside. Then you can go to step 3 to do inverse Laplace transform. All right. Yeah. So now we go and find this K1 and K2. So we, of course, you need some kind of condition to find, right? So then we check our question here. So we realize that our question, just now we used initial conditions already, right? But we still have 2 boundary conditions which we haven't used. All right, so now is the time to use. Yeah, so now let's go and use. Okay, now when you want to use, you realize that this one is a small u and it's a 0t. Right? It's a small u. Whereas our this one is a capital U. Right? This one is a capital UXS. All right, this one is a small u, and then you got your x as some value, and then here is t, right? So directly you cannot use because it's different. This one is a small u, this one is a big U, right? So we can't use directly. So what we do here is we go and Laplace transform the boundary condition. So you Laplace transform. Okay, you Laplace transform the boundary condition. Then your U0t, right? You Laplace transform, your small u, of course, your Laplace transform is respect to t. So your small u becomes your capital U, your t becomes your s. Then you wonder, then this x equal to 0, eh? Now this one no change because your Laplace transform is respect to t. Okay, so your x no change. Okay, so this is your left hand side. Then your right hand side, this one 0. So your Laplace transform 0, then you give you 0, right? So similarly, this one you also Laplace transform. Then you get your capital U 1, and then your t becomes s. And then your right hand side is 0. Is it okay? All right, everybody all right or not? So everybody okay, huh? Yep. So okay already. So now we shall use this one and this one. Okay, so if we use this, that means inside number 4 here, you are going to substitute your x as 0. Okay, yeah, and if you use this inside number 4, that means you are going to substitute the x as 1. Okay, not? Yeah. So we go and do that. So this one will give you some equation. This one will give you some equation. So 2 equations, then you also have 2 unknowns, right? So we should be able to solve the K1, K2. Okay, so this is my, just substitute inside, we get this. So that means I can express K1 in terms of K2, right? And then I use another condition. Well, that will give me like this. And then I use this one. K1 is minus K2, right? Go and put inside so that I can eliminate one of them. Yeah. So, okay, just write it nicely. Okay, then I go and substitute the K2 as minus K1. So that's why I get to here. Okay, so from here I should find K1. Yeah, so I can get K1 already. All right, so you see here, here you got two items, right? So you got K1 and multiply by this thing, right? So there are two things, multiply together. And the outcome is 0. So then you know already, when you have two things multiply together and you get 0, so that means one of them must be 0. All right, so one of them must be 0. So is K1 0 or is e to the power of s equal to e to the power minus s? Is K1 0? K1 equal to 0, or is e to the power of s, power of s, is it equal to e to the power of minus s? So which one is it? So which one do we take? Which one do we take? So this one or this one? Yeah, class. Let me ask you, which one you take?
K1.
Why you don't take e to the power s equal to e to the power minus s?
That one need to hold for every value.
That one what?
That one must hold true for every value of s.
Oh, yeah, that's right. Because this e to the power s equal to e to the power of minus s. Well, actually, you know that the s actually is a variable, right? So you know that this one cannot be true all the time. All right. So in fact, this one, I want to type here. This one is true only if s equal to 0. Right, so in fact, this equation here, this particular equation, this, I see, I cannot for you. Okay, so in fact, this one, this equation here is true only if s equal to 0. All right, so it's not for all s. So that's why you can't have this. So the only choice is K1 equal to 0. All right. And therefore, you can also find your K2. K2 also 0. All right, so K1, K2 both 0. Well, so now what you do is you substitute K1 0, substitute K2 0 here. So that means you have found the unknown constants already. All right, and then you can now get your UXS. Yeah. So now you put in your K1, K2, and you finally obtain your UXS. All right, so this is our summary here. You have done step 2. You have obtained your UXS already. All right, there's no more unknown constants. So now it's time for us to do inverse Laplace transform. All right, so when you do inverse Laplace transform, your aim is what? Your S, you want to change to T. Is it okay? Right? So when you're looking at this thing, you want to inverse Laplace transform, right? Now you see that here, you only look at the terms in S. All right, now the terms in S is actually this term. Why like that? So the terms in S, cannot. So the terms in S, well, you know that it's only this one, right? It's 1 over pi square plus s square only, right? What about this term in sine pi x? This term in sine pi x. Now this one is in x. All right, so when you're doing this inverse Laplace transform, this one is like a constant. Okay, so sine pi x still there. So basically you're looking at constant times this. So actually you're concentrating on this, right? So let's see our Laplace table. This is our Laplace table. Here is our Laplace table. So what do you all think? Can we see? It's one of these. Don't know whether you all see or not. Which one? 1 over pi square plus s square. Which one you want to use?
Sine.
What?
Sine.
Yeah, you're going to use sine. You're going to use sine. All right, because you see here, you get this one. Of course, the numerator here is omega. Omega over s squared plus omega squared. All right, so it fits in very nicely. So you just need a pi on top, right? Your omega actually is pi. So if you need a pi on top, then what you do is that you go and divide a pi outside law. So that's why you see, I get a 1 over pi. Then after that, this one is just your sine omega t, which is your sine pi t. Okay, so that's why you get this. Then your sine pi x there, sine pi x is here. Okay, it's just like a constant multiple like that. Is it okay? All right, so that completes this question. Any problem? Okay, so no problem, right? Yeah. So this question, do you all find it complicated? Do you all find it complicated or simple?
Troublesome.
Troublesome, yes. So actually we noticed that in these 3 steps here, usually step one can do not difficult. Okay. Step 2 can be difficult because it depends on the ODE. Right. So if the ODE is like what we have just now, second order non-homogeneous, so you can see that take quite a bit of effort to go and find the solution, right? And then, of course, the third step, when you are doing inverse Laplace transform, it can be challenging also. Sometimes the function, wow, very difficult one, right? Then don't know how to do inverse Laplace transform, right? So step 2 and step 3 can be difficult. Okay, yeah. Okay, so now let's go and do the next question. Yeah, so this is actually the next question. The partial differential equation given by this. Okay, so we see this PDE, right? With initial and boundary conditions given by this one and this one. Okay, so there are 2 initial. This one is initial condition. This one initial condition, and the other one, well, actually, you want to call both initial condition also can. This is when t is 0. This is when x is 0. Okay, yeah. So what do we want to do? We want to solve for yxt by method of Laplace transform. Okay, so we'll do this one. Okay, by method of Laplace transform. All right. Now let's go to our summary. Is this suitable to use a method of Laplace transform? Okay, let's see our summary. Yeah, I believe it's page 2. Yeah, so let's see. Laplace transform is for linear PDE. Okay, invariant in at least one independent variable. All right, so let's go to our question. So this one, is it linear? This one linear or not? Linear? Linear? Linear or not?
Yes.
Yeah, this one is linear. Okay, because you can see that every term is, well, last time we said linear is only u, right? Here, of course, they are not using u, they are using y. So it's only y. First term only got y. Second term also only got y. Okay, x squared is a independent variable. All right, so the x is an independent variable, so it's okay. All right, it's still only y. So it's linear. Then the next thing is it invariant in at least one independent variable? This one is invariant in which independent variable? On the other thing, you look at the coefficient of the y term.
T.
Invariant in?
T.
Yes, invariant in t. All right, in fact, it's a variant in x. All right, because of the x square here. The coefficient here got x square, right? So it's variant in x, but the coefficient doesn't have t, so it's an invariant in t, variant in x. Well, that's fine. Variant is x is okay. All right. as long as you have an invariant in one independent variable, right? Okay, so now we are going to apply this Laplace transform method. Yeah, so our summary of our method is here. Okay, let's go and do Laplace transform to the whole equation. Okay, so you see solution is here. This is a partial differential equation, right? Okay, so let's get our notation correct first. So our unknown function is a small y xt, all right? And after Laplace transform with respect to t, I will call it capital Y xs. Okay, yep. Okay, now I'm going to Laplace transform with respect to t. With respect to the independent variable that the PDE is invariant in. Okay, all right. It's not say every time with respect to t, but it just happened that here, this PDE is invariant in t. All right. Okay, let's go and do Laplace transform. Okay, Laplace transform. Now let's look at first term. Now, first term, y subscript x. You all know what's the meaning of y subscript x, right? Del y del x. Yeah. So the derivative is respect to x. Now, derivative respect to x, right? But you are doing Laplace transform with respect to t. So the derivative respect to x is still there. Okay, you see the subscript x still here. Okay, but what you do is that the small y, you go and Laplace transform so that it becomes the big Y. All right, so this is a del big Y del x. Is it okay? So this one will give you this. All right, so give you this. Then the next thing is minus x squared. Then you got y subscript t, right? Y subscript t means del y del t. Okay, now x squared here considered like constant. So this constant still here. And then the y subscript t, derivative respect to t, you want to Laplace transform. So we refer to our this well-known formula. Okay, now I should look at this. Laplace transform y prime t, differentiation with respect to t, right? So I should get s ys. Okay, then you see s capital ys. Okay, s capital y. Well, here only s, but here we actually got two variables, right? So it's actually s. Okay, and then minus y0. Now the y0 here, the 0 is when t is 0. Okay, so over this side is y x0. All right, when t is 0. Is it okay? All right, so this is our left hand side. So this one give you this. So this is our yt. Our yt give you this one here. Then here, of course, 0, you go and Laplace transform, right? So you will still give you 0. Okay, yep. Okay, then, okay, here there's an initial condition, yx0. So that one actually is given. Yep, then you see it's still given, right? Yeah, so we can use it. So I'm going to substitute inside. And then after you substitute in, this is what you have. All right, and then you realize that, oh, look at this. There is no more derivative in t. In fact, t disappear, right? Now you only have derivative in x. That's from here, yx. That means del y del x. Right? So the derivative is only in x. So therefore, you can consider this as an ODE in x. All right, and I'm going to solve this. Okay, now, yeah. So actually, we are here. We already got the PDE transformed to an ODE. So this is our ODE. So we are going to do step 2. Go and solve this ODE. So we are going to get the capital Y XS. Okay. Now this one is easier to solve because you look at it now. This is a Y term, this is a Y term, right? And then here is 0. This one is 0. So this is a homogeneous ODE, right? So in fact, this is a homogeneous. Yeah, it's a homogeneous ODE in X. Yeah, so to solve this is easier because you no need to consider particular solution. All right, and I can see that here we can actually separate the variable. So I actually go and write this out, dy dx, okay, because you consider as ODE, right? So instead of del x, you change to a d dx. And then this term, I just bring to this side. Yeah, so I can see that I can bring all the capital Y together, right? Yeah, so I will get dy over y, then here I got x squared s dx. Okay, so then what we do is that just go and integrate both sides. Okay, so you see this is the integral lah. Okay, so integral. Hey, now integral your left side, right, which is dy over y, integrate. So this one you go and integrate, you will just get the ln y. So okay, integrate, get the ln y. Then here how to integrate? This is an x squared s dx, dx. So that means here only your x square is like a variable. Your s is like constant. Okay, so that's why you get x cubed over 3, and then your s is like constant, right? Then you plus c. Is it okay? Any questions here? Yeah, so your c is a constant. Now, although we say c is a constant, but it may involve s. All right, so maybe I write here. Your c is a constant, right? C may involve s. Okay, yeah. So now, let me go and find the capital Y. Y will be e to the power of this, right? Yeah. So go to the next page. So capital Y is e to the power of that. Then you wonder, this a don't know where it comes from, right? Oh, I know already. Y is e to the power of this. So e to the power of this thing times e to the power of c. So e to the power of c is another constant, right? Yep. So I call it a here. Yeah. So that is the a here. Is it okay? All right. So I got the a already. So this a is a constant. Of course, may involve s. Okay. So now I need to find out this constant because I can't do inverse Laplace transform yet. Because this a is unknown. All right, so let's go and see got any condition we haven't used or not. Okay, so if you look at your question, well, you have used this yx0, right? So now you're left with one, which is this y0t equal to ut. All right, so I'm going to use this in here. Right, so I'm going to use this in here. So can we use directly? This y0t equal to ut, can we use directly inside? What do you think? You can use this one inside here directly or not? Yeah, class. So what do you need to do?
Laplace transform.
So you need to Laplace transform this condition so that your small y becomes big Y. Then you can use. All right. So here we are going to Laplace transform. Right. Transform. Yeah. So Laplace transform. So your Laplace transform, then your small y becomes big Y. Yep. So this is your small y becomes big Y, and then your t becomes s. Then your zero is x equal to 0. So that one no change. Okay. Yeah. And then your ut becomes 1 over s. Right. So now you can use this in this. So now you can just go and substitute this from here, right? And then you can use here. So what you're going to do now is you're going to substitute the x as 0. Okay, substitute the x as 0. And when you do this, you will get, you will actually get a, right? Then your x is 0, that means you will get a here. Then over here, y0s is 1 over s. So immediately you get your a. Yeah, so this is your a. All right, and then what you do now, your this a, put inside your this solution here. This is a general solution, and then you get your this thing here. All right, so this is finally the solution of the ODE. Yeah, this one, what I highlight here, this one, right? is actually the solution of this homogeneous ODE. Okay, not right. And you can see that there's no unknown constant now. Right? So we actually done step 2 already. We already got the solution. So now we can do inverse Laplace transform. Of course, you want to change the S back to T. Okay. Hey, so now you look at this. Your aim is to change the S back to T. So this X cube here is like constant. Is it okay? Yeah, the X cube here is like constant. So therefore, your this one is actually like this. It's like 1 over S. And then you got e to the power of, so this one is multiplied. Yeah, 1 over S multiplied by e to the power of your 1/3 X cube is like constant. Yeah, it's like constant S. All right, so the C here is like constant. So your C is like X cubed over 3. So it's actually this form. All right, so we go to the Laplace table. Now, this one is the Laplace table. So what do you think? Which one to use?
Unit step.
And
the time shift.
Oh, okay. So it looks like it's not here. Yeah, it's not here. You don't have anything like that. So if we go to the next page, then we see that, still not yet next page. This one is next page. So we find that it's actually this kind of form. Can you all see that it's actually this form, right? It's actually this form here. Then you get e to the power of something s, right? And then you got your fs. Your fs here is of course 1 over s, right? So according to our time shift, this is what we have. Right, so this is actually the answer. Okay, so your capital F is 1 over S, which means that I think everyone can memorize 1 over S, then you know that your small f is UT. Yeah, so your small f is actually UT. So let me type here, your small f. Your small f is actually, small f is actually UT. Yeah, the unit step function. Okay, it's actually UT. And then your answer, I mean, if you follow here, is a UT minus T naught, UT minus T naught, right? And I think I told you all that UT minus T naught times UT minus T naught is what now? Yeah, UT minus T naught times UT minus T naught is equal to what, class? See, you know or not? If you have UT minus T naught, all right, according to your this time sheet, right? UT minus T naught times UT minus T naught. What is it equal to? U times U is what? U times U is U square, What is U times? U times U becomes 0.
I mean, don't know.
Oh, don't know. U times U is U. This is very intuitive. Because you see, when T minus T naught is 1, that means this one T minus T naught also 1, right? And that is when T more greater or equal to T naught. So it's also the same as this, right? When T greater or equal to T naught, this one also 1, right? If your T is less than T naught, your this one of course 0, then times 0, then also 0, right? And here, when T less than T naught, this is also 0. So 1 times 1 is 1, 0 times 0 is 0. So U times U is U. Is it okay? All right, so that means you don't need to write 2 times, you just write once is enough. Okay, yeah, now let me ask you another question. What is our T naught here? What is our T naught here? T naught here, here is e to the power of 1/3 x cubed s, right? So can you tell me what is the t naught?
Minus 1/3 x cubed.
Yeah, it's a minus x cubed over 3. Can you all see? There's a minus. So your t naught actually is this. Okay, then you just put inside. This is actually your answer already. So therefore, you just get your yxt is u t minus t naught. This is your t minus t naught. Okay. Yeah. So that is the answer. Any problem? No problem, right? Okay. Okay, no problem. So let's go and do one question here. All right, so this is the question. So here is the question. So we have ft is this function here. No, this one is not a question. This one looks like solution. And where's my question there? Yeah, this one is the question. Okay, so consider the following function. So your ft is like that. Okay, t from 0 to pi. What do we want? So we want to find the half range Fourier cosine series. Okay, half range Fourier cosine series of ft. All right, yeah, half range Fourier cosine series of ft. Right. So let's go and recall what is this half range Fourier cosine series. Right. So go and recall this one half range series. Okay. So half range series is actually like that. So we got a function is defined from t equal to 0 to p. All right, it's not known to be periodic. That means they don't tell you that it's periodic. And then they want you to find this half range series, right? Okay, so this one, look at the box here. So the first one, the first formula is actually the half range Fourier cosine series because only involves the cosine. Okay, and then the second one is called half range Fourier sine series. Okay, right. And of course, the principle behind how we get these two is actually we go and extend the original function. Okay, when you see the original function is from 0 to p, right? Yeah. So that is the diagram I show you, all right? And your ft is only from 0 to p. So they say they didn't tell you that it's periodic. Okay. Now, if not periodic, then how can you still go and write down something like Fourier series? So therefore, what you do is you do extension. You do extension to the part minus p to 0. Okay. Yeah, you do extension. Now, when you do extension, there are two ways you can extend it. You can extend it to become an even function, or you extend it to become an odd function. All right. If you extend it to be an even function, the outcome will be called Fourier cosine series. You will get a half range Fourier cosine series. All right. If you extend it to be an odd function, which is like that, okay, then the outcome will be Fourier sine series. Okay, so it's like that. So since the question here, they ask for half range Fourier cosine series, right? So then we'll do this. We'll do this. So we make it an even function. Even function. Okay, from minus p to p. Even function in minus p to p. All right. Yeah, so it becomes an even function in minus p to p. All right. Yeah. So we extend it, we make it an even function in minus p to p. And then you assume that this is a one period of a periodic function. And then you go and write down the Fourier series. Okay. Now, because this one is even function, right? In minus p to p. So the period is actually 2p. So you can write down the Fourier cosine series. It will only involve cosine term. All right, and that is exactly this formula here. The formula here actually is exactly the same as that of Fourier cosine series. It's okay, but of course you realize that Fourier cosine series is valid for all t, but here it is only valid for half range, t from 0 to p. Is it okay? Yeah. So this is our half range Fourier cosine series. All right. So this is the one that you want. This is the one that the question is asking. All right. So therefore we put here half range Fourier cosine series. Now look at the solution here. Okay, here involve the parameter p, right? What's p? Oh, p is what? The original function defined from 0 to p. So if we look at our original function here, it's defined from 0 to pi. Can you see I highlight this pi here? So this pi is our p. Got it? Okay or not? Yeah. Okay. Yeah. So since we got the p already, we just use this formula, right? Which is the same as that of Fourier cosine series. Just that now we make it half range. So it's valid from t from 0 to pi. Okay. So the A0 and the AN formula is exactly the same as the Fourier cosine series. I believe it's here. This one, Fourier cosine series. That is what I showed you last time, right? So this is the formula. So you see, I use the same formula. There is my A0, right? So A0 is like that. Same. Yeah. So now I just go and put the P inside. Okay, so then becomes like this. All right. Then you just go and integrate. Yeah. So integrate, you get this. All right. So the next thing is I'm going to get this AN. AN, see the formula I use is exactly the same as this, right? Okay, put in your P, put in your F, then you get this thing, right? Oh, wow, then you see this, don't know how to integrate, right? Now, of course, here you want to multiply in first, right? You want to multiply in. So I think first term cosine nt, we know how to integrate, right? But second term, sine something, cosine something, right? Now, how do we integrate? Yeah, how to integrate? So let's see here. Oh, I see. Here they actually give us a formula here. All right. So you see, sine times cosine can be written as sine something plus sine something. Because this one is a plus sign, so then we can integrate term by term. Yeah. So let's go and do that to here. So this one here, I leave you to go and work out. So I just go and write up like this. Okay. So this one you go and integrate, go and work it out. Okay. So using this, so we'll get this thing. Yeah. Oh yeah, this answer, I'm not so sure whether is it correct or not, or there's some minor sign. Okay. Yeah, there could be some minor sign missing here. All right, but you get the idea, huh? Okay, so I actually got AN already. So now I got A0, I got AN, right? So let me put it into my this half range Fourier cosine series. Okay, so I put in your A0, put in your AN, and it's a half range, right? Okay, so that completes part 1. Now, part 2, write down the first 4 non-zero terms. Okay, that's easy. First 4 non-zero terms, right? Now here, you already got 2 terms. Now here you got 1 minus 2 over pi, right? So this is considered 2 terms already. So you just need another 2 terms here, okay? So you just try when n is 1, when n is 2, then you will be able to get. Okay, right. So this one, not difficult. Now we come to part 3. Now part 3 is like this. Sketch. Sketch. Sketch what? Sketch the Fourier series obtained in part 1. Okay, sketch the Fourier series obtained in part 1 for this range of t from -3 pi to 3 pi. All right. Actually, part 3 is the difficult part. Yeah, part 3 is the difficult part. So we actually test our concept of half-range Fourier cosine series. Right? So if we just look at the question itself, sketch the Fourier series, right, obtained in part 1. You want to sketch. Then you can go and look at your Fourier series in part 1. Fourier series in part 1, no? Now this is the one, right? Then you see, oh wow, this one got infinite number of terms that go and sum up. So if we just look at it like that, you know, then of course you wonder, wow, I don't know how to sketch, right? Because there are infinite number of terms inside. Okay, so you definitely cannot sketch by looking at this expression. Okay, you can't do it. So what are you going to do then? Y'all have some idea or not? So y'all have some idea?
Is it term by term?
Term by term. But this one is an infinite number of terms. So how do you term by term? Until infinity. So that means you cannot look at this to sketch. Okay. So if you don't look at this to sketch, now you see what they write here. Ft, that means your function is equal to this Fourier series t from 0 to pi, right? So do you know the expression of Ft or not? If you don't look at the Fourier series, this is actually your expression of Ft, right? Are you able to sketch this from 0 to pi? Well, maybe can now, but now not so difficult. Can y'all see? Can y'all see this? Can, right? So you can do this, right? Yeah. Yes, we can do that. All right. So if we go and sketch, that partner. Let me go and sketch here. Okay. Yeah. So this is my 0. And then this is my pi. Okay. How to sketch? So if you substitute 0, you will get 1. Okay. So I get a point here. You substitute t as pi. Then I get 1 minus 1, then I get 0. Okay, so you get 1 point here, 1 point there. Of course, it's not a straight line. So if you go and sketch, you will find that it's actually a curve like that. Okay, it's a curve like this. Right now, yeah. So this is the curve like that. Okay, so you have got the part 0 to pi. Is this okay? So this 0 to pi actually is just this function, right? Okay, so how do you make it until -3 pi to 3 pi? Well, now you've got 0 to pi already. Then what do you do?
By symmetry, then extend.
Symmetry. Why do you say symmetry there? Because we are doing a half-range Fourier cosine series. All right, remember just now our summary, we said that how do you do half-range Fourier cosine series? You have your function here. Suppose this is your function. Of course, just now ours one is not like that. It's another curve. You extend it, make it an even function. All right, you make it an even function, and then you say, oh, you got an even function in -p to p. You assume that this is a 1 period, and then you go and write the Fourier series, right? Okay, so you actually want to make it an even function. Even function, and that is 1 period of a periodic function. Okay, you want to make it an even function. So now if we come to this, how do you make it even function? Then you just put like this, because you know that even function is symmetrical about the vertical axis. Now, of course, the drawing here is very beautiful. Yeah, so this is a -pi. Okay, so now you've got an even function from -pi to pi, from -p to p. Okay, And you assume that this thing is periodic, right? That's how you go and write down your half-range Fourier cosine series, right? So when you want to extend this one, if it is one period, do you know how to extend? Know how to extend or not? If this one is one period, do you know how to extend? Do you know how to draw? Know how to draw or not?
Copy and paste.
Yeah. So if you go and draw, then you get something like that lah. So just now you only have from minus pi to pi, right? That's one period. Then you go and draw another one. Then there'll be until 3 pi. You draw here, draw another one. There will be until minus 3 pi lah. So it's like this. Okay. So you get it? All right, now. Okay, y'all. Yeah, so this part 3 actually is to test our concept. Yeah, the concept of half-range Fourier cosine series. How do we get the Fourier cosine series? We go and extend the function, right? Extend it to become an even function, right? So that is what we do. So initially we only have this part here, right? So we go and make it even, right? So it looks like I cannot type. I cannot, can. Then I make it even function, then become like that, right? So it's like this. Then because this thing periodic, you assume periodic. So that's why you can draw a few patterns here. Okay, now. So okay, so this one done. Yeah. So now let's take a look at another problem. So this is another problem. So the question is on your left side. Okay, so here is the question. Use partial fraction expansion. Find the inverse Laplace transform of this expression. Okay. Yeah. Okay, let's go and do part A. Use partial fraction. Go and find the inverse Laplace transform of this. You see, they give you a hint how to find use partial fraction. Okay, right. Okay, so let's go and do partial fraction. Now, this thing, you want to do partial fraction. So obviously, you cannot do the e to the power minus 3s. E to the power minus 3s, you got to take it out. Okay, so actually you just do the 1 over s times s squared plus 1. Is it okay? So this one you do partial fraction. How you do? This one definitely you can factorize, right? You got an s, you got an s squared plus 1. And s squared plus 1 cannot be factorized further. Okay, so when you do partial fraction, you will just have two terms. Constant over s plus, now because this one is s squared plus 1, I've got s squared, right? So you got bs plus c. Is it okay? Yeah. Then you go and find your ABC, your constants. Then you will get to this. All right, And then after this, now now that you got this already, then you put inside here, then you got times e to the power minus 3s, right? So then you go and do term by term. So inverse Laplace transform this, inverse Laplace transform this. All right. Then when you see this, you see, wow, got e to the power something s, right? Wow, looks like don't know what kind of shift. I cannot remember the kind of shift. Can you all remember? Now maybe you can remember. So you can remember. There's a chat here. Let me see what you say. For exam, what is it? Do you need to memorize trigo identity for exam, or will they be given as shown in your examples? If a simple one, you need to know, right? If a more complicated one, then they will give. Okay, so I hope that is clear. Okay, so now we come to this. Okay, got another one. Got another chat. Okay, this one is thank you. Okay, so yeah, now we want to inverse Laplace transform. So we look at this. You kind of familiar with the formula, just that maybe you cannot memorize only, right? So you know that, I better go and look at this. So we find that this one, it fits the time shift very nicely. So you see, you got, in fact, both of the terms, they got e to the power of something s, right? The t naught here is definitely 3. Yeah, t naught is definitely 3 lah. So you observe something, outside your draft, your exam booklet on the other side is a draft, right? Except for your draft work, right? So then you can put, t naught is 3. And then you have your fs. You see your fs, you have 2 terms, 2 different fs, right? So your first fs is of course very easy. It's just 1 over s, right? Yep, just 1 over s. So for the first term, well, 1 over s, actually you can straight away, lah. Your ft is, this one I think I no need to go for exam. I also can remember. So I know it's a ut. Don't need step function, right? So for the first term is it's a ut minus t naught, ut minus t naught. And then I think today we talk about this, right? U times u is u. So for the first term, it's actually a ut minus 3. All right, yep. So it's actually ut minus 3. Look at this one here. It's just ut minus 3. Okay. Yeah, let me highlight. So actually for the first term, this is just your answer. It's actually ut minus 3. So that's your answer. All right. Now for your second term, your capital F is different. All right, capital F is different. So that means your small f will also be different. So this one is s over s squared plus 1. All right, yeah. So this one, do we know the ft? Well, I think also look familiar. Yeah, this one also looks familiar. So if we go up to C, s over s squared plus 1. Yeah, can you see or not? Can you see s over s squared plus 1?
Cosine.
Which one?
Cosine.
Yeah, actually it's the cosine, right? They see here. S over s squared plus 1. Right? Yep. Yeah, this is the 1. So your omega is 1. So I'm just going to get cosine t. Yep. So this one is just cosine t, lor. Cosine t. Yeah. So therefore, according to our, it's a time shift. Yep. Time shift. Time shift. So it will be a cosine t minus t naught and then ut minus t naught, right? So let's see whether this is like that. Yes, it is. So it is cosine t minus 3 ut minus 3. Yeah. So you can just pull out the ut minus 3. Yep. Okay. So any problem here? Right, so this one no problem, right? So let's look at another part B. A certain linear time invariant dynamic system is described by this differential equation, where xt is the input function. Okay, so we want to find the transfer function of the system. Is the system stable? Justify your answer. Okay. Yeah, so first thing you want to find transfer function. Okay, now transfer function, as we know, transfer function is what now? You still remember or not? Transfer function. Transfer function is equal to what put over what put now? Yeah, class. What is it?
Output over input.
Output over input. Okay, yeah, so it's output over input, right? So output there is the y. Okay, input is the x. Yeah, so this one is actually equal to, because we know we want the s domain one, right? So it's a ys over x. It's okay. All right, so this is the transfer function. Yeah, this is a transfer function. Okay, so let's go and find this transfer function. Okay, so here is our differential equation. So to find the transfer function, we need to set all the initial conditions to 0. Okay, so this is when you want to find transfer function. All right, so what we do here is, because we want S domain, so this ODE will just go and Laplace transform. Okay, Laplace transform the whole thing. So you will just get like that. Okay, so your d2y dt square will give me this bracket here, here. Then your dy dt will give me this second bracket here. Okay, and then your yt there will just give me the -6 ys. All right, then your xt will just give me the xs. It's okay. This is after Laplace transform. Yeah. So over here, of course, you can see those initial condition, right? Your small y 0, your small y prime 0. All right, so we are going to set them to 0 because we are finding transfer function, right? You just set them to 0, then you get this. Then I think can already. I think you can get y on one side already, right? Then you just go and get y over x, just manipulate. So this is your y over x. So this is your transfer function, all right? So that is your y over x. Is it okay? All right, Okay, so this is what you have. And we find that, this one happened to be able to factorize. All right, happen to be able to factorize. Okay, now the question asks us, is the system stable? All right, now how do we see it from transfer function? Now how the system stable or not? How can we see it from the transfer function? Now actually in our previous tutorial, last time they asked us to get the small yt, right? And then from there we go and see the small yt stable or not, right? Yeah, remember? So actually how here, here, if we want to get the small yt, we can also get the small yt, okay? That means you got your ys here, then equal to transfer function times xs, right? And then you go and inverse Laplace transform, okay? All right, so actually here, although we don't know what is the xs here, it's not given, right? But in the process of inverse Laplace transform, we know that it has to, this one will come into play. All right, this one will come into play. So the inverse Laplace transform will depend on the form of this transfer function also. All right, and from here, because we can factorize into s minus 3, s plus 2. So when we want to do Laplace transform, rather inverse Laplace transform that time, then you know that we always go and do partial fraction, right? So we'll have a constant over s minus 3, right? And then plus another constant over s plus 2. All right, then you want to go and inverse Laplace transform. And if we look at these two terms, 1 over s minus 3, 1 over s plus 2, I cannot memorize. I need to look at the appendix. Now, if we look at our appendix, so far away. Okay, here. Okay. Now, it is 1 over constant over s minus 3 or constant over s plus 2. So that means it's this exponential, right? So it is this one that we are looking at, right? So then we know that it's e to the power minus at. Okay, so your first term actually will give you e to the power of 3t, correct? Your second term will give you e to the power of minus 2t, right? Okay, so what we are more interested in is the e to the power of, from this 1 over s minus 3, it will give us e to the power of 3t. Yep. Can you all see that? It's from this exponential here. Because here your a is minus 3. So you get e to the power of minus 3t. Yep, so that means e to the power 3t. Whereas this one there will give us e to the power of minus 2t. All right. So this e to the power 3t here, it will go to infinity. when t goes to infinity. All right, so that will make the yt unstable. Your e to the power minus 2t here, this term is okay because it will go to 0 when t goes to infinity. So this term all right, but this term not okay. All right, so you will just make the yt unstable. So that's why we say that this one, the system will be unstable because the transfer function has this term, all right, which will give rise to this term, e to the power of 3t, okay, and that will make it unstable. All right, now, so this is part B. Yep. Yeah, so that's part 1. Now, okay, let's look at part 2 here. Now, part 2 here is like that. So now they give you your xt. Now, part 2 here, actually, they give you the xt and ask you to find the yt, right? So here they give you the xt is 2ut. And they also give you some initial conditions and ask you to solve for yt. All right, okay, so let's go and do that. So this time it's not finding transfer function, but the way of doing is about the same. Just that here, your initial conditions are given and they need not be 0. Right, so if you go and do that part, so you take Laplace transform, same as before, just that now your initial conditions are different. Right, so you go and substitute in the initial conditions now. Okay, go and get your ys, right? And then after getting ys, you want to get yt. Okay, so this is your ys. Well, you want to inverse Laplace transform, right? Yep. Now here your xs is known, okay, because they give you the small xt. So your xs here actually is 2 over s. All right. So that's why you see here your xs is 2 over s. Okay, so now I get the ys already. I want to inverse Laplace transform. And of course, if we look at this, how do you do inverse Laplace transform? Any suggestion how you do inverse Laplace transform here?
Partial fraction.
Yeah, so we just go and do partial fraction. All right, partial fraction. Then very easy already, right? You just get the capital YS, and then you can get the YT. Okay. Right. So this YT that you obtain, stable or not? Stable? Stable.
No.
Okay, so stable or not? Actually, it's no. Right? From where? From which term is not stable?
E to the power t.
So actually, it's from this term. You get e to the power 3t, right? So when t goes to infinity, this one goes to infinity. All right, all? Okay. Yep. Okay, let's go to part C. Find the Laplace transform of this. Well, you notice that here A, B, C, they are all different. They are not connected. Okay, now we just want to find this Laplace transform, right? Okay, Laplace transform. Well, there are 3 terms here. Then outside multiply e to the power minus pi t, right? So first thing we do is we go and separate out the 3 terms. Okay, yeah, separate out the 3 terms. Then try to Laplace transform. Wow, this one also look familiar because got e to the power something t, right? So let's go to our appendix. Don't know time shift or frequency shift. So what kind of shift do you all think?
Frequency.
Yeah, it's a frequency shift, right? Because you can see that the function is of this form. You want to do Laplace transform, right? Then you got ft and you got e to the power of something t, right? And you can see each of these terms, they are all like that with different small f. Yeah, you can see that here your small f is I cannot. No, I cannot. It's big. So this one here for the first term, this is a t square, right? For the second term there, the small f is just a t. Yeah, just t alone. And then for the next term, actually is sine t. And for each of this, whether t square lah, or t lah, or sine t, do we know the capital? Do we know the capital F leh? I think we know. Okay, I think we know. T square, t square, t square is it here? T square is not here. Funny. How come t square not here? Yeah, it's here. T square actually is here. All right, then you see t square is here. Now you see there's a half, right? Half, never mind. The half you just bring to here. So this is a 2 over s cubed. Okay, so for the first term, actually it's 2 over s cubed. Then t, do we know t? Yeah, we know t. Here, this one t. So there's 1 over s squared. And sine t, of course, we know. Then here, sine t, that's number 7 here, right? So sine t we know. All right, so we know the capital Fs, right? So that one not a problem. And this frequency shift is saying that the answer is what now? The answer is Fs plus S0. Okay, now the S0 in all these cases, can you tell me what is the S0? Yeah, class, tell me what is the S0? Anyone?
Pi.
Yep. It's pi. All right. Yep. So it's pi. Okay. So that is your pi here. So that's why you see that by our frequency shift, this is my ft. You know, this is a capital Fs, and then your s there want to shift to s plus pi. Okay. Yeah. That's why you get all these. And then this is what you have eventually. So it's F, capital F, and the argument is S plus S0. So there's your S plus pi. All right. Okay. So any questions? So just to check with you again, my microphone, is it loud and clear?
Yes.
Oh, okay. Yeah. So no problem, right? Yeah. Yeah, so I complete the question already. And with this, we also complete the whole tutorial. All right, now, class?
Yes.
Okay. All right, so I wish you well. Get good results in the exam.
Okay, thank you, Prof.
Okay. Yeah, thank
Thanks,
you, everybody.
Prof.
Okay, thank you. Bye-bye.
Bye.
Bye-bye.
Bye.
Yeah, good night.
Good night.
Good night.
Yeah, good night.